Okay, in this video we are going to start applying what we've learned about derivatives into some story problems and some real life application to how we use a little bit of calculus in real life. So far we've just been focusing on the process. Now we're going to start focusing on applying what we know about derivatives and what they mean and what they do. But first I want to show you one thing. This first example, we're going to take the derivative with respect to t of this problem right here. Well, you may think that's funny is because we don't have a t in that equation. So we're going to implicitly find the derivative dy dt, all right, and they give us a certain set of conditions. When x equals 1, dx dt equals 2, and x equals 1. When this comes is important is when we're talking about related rates, and that's what we're going to be talking about today in this video and these story problems. When we have rates, anyway, and we're looking at the derivative with respect to time as certain things happen, and you'll see that farther here in the video. But this first example, I want to take the derivative with respect to t. Well, anytime we're taking a derivative with respect to anything other than our variable, we have to do the chain rule, which means we have to take the derivative with respect to y. So the derivative of y is just 1. All right, and then we need to take that times the derivative of y with respect to t, dy dt. All right, we need to take the right side's derivative as well. So anytime we're taking the derivative of the variable, so we're taking with respect to t, but that our variable is x, we have to do the chain rule. All right, so take the derivative with respect to x, which is 2x, and multiply it times the derivative with respect to t, so dx dt. And then obviously then the derivative of just 3 is 0. Derivative constant is 0. All right, well, we want to find what dy dt is. They've given us some certain conditions. They say x equals 1, so we can go ahead and plug 1 in for x. They say dx equals 2. So we're going to go ahead and we're going to plug that in there too. So we'll be able to find what dy dt is when x equals 1 and dx dt equals 2. So we have 2 times 1 times 2. So our dy dt, our change in our y with respect to t, is going to be 4. I just wanted to show you that quick example because that's going to come into play here when we have a certain set of conditions here in our next example. So in our first example here, we're looking at a pebble that is dropped into a calm pond, causing ripples, all right, in the form of concentric circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of distributed water changing? We have to decipher a little bit about what we're finding. The question we're finding is we're looking for the rate of the total area of the circles, the ripples, all right? So we're looking for the rate of the total area, and we learned that when we take the derivative, we're finding the instantaneous rate of change. So in fact, we're looking for the rate of the area. So dA dt, we're looking for the rate at which the area is changing. I'm using A for area with respect to time. All right, so anytime it's going to say the rate is probably going to be a derivative, because when we take derivatives, all right, we're finding the instantaneous rate of change. So we're looking for the instantaneous rate of change of the area. So we're looking for dA dt. What else do they give us? All right, let's see here. Then they tell us the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. There's that word again. There's that rate word again. All right, when they say rate, all right, we're talking about a derivative. So we're talking of d something, all right, with respect to t. Well, what are they talking about? They're talking about the radius. They're talking about how the radius is changing. So I'm going to use r for radius, dr dt, and that equals 1 foot per second. Okay, good so far, hopefully. And the next thing, what they're asking though is, well, where should we start? Where's the formula? I have no idea. All right. The formula we should probably use, since we're dealing with area, is the area of a circle, right? So area of a circle equals pi r squared. There's one more condition that they gave us. It says when the radius is 4 feet, that's when they're looking for dA dt. So we don't know this, but we know that the r equals 4. Okay. So we're looking for dA dt. I want to take the derivative with respect to time because the ripples are changing with respect to time. You know, if you drop a pebble in water, all right, the farther it gets out, the longer that ripple goes, the wider it gets, the bigger the area of the circle. So I would take the derivative with respect to t. So dA dt, derivative of A is just 1. All right, and I need to multiply that by dA dt. Equals, pi is just a constant, don't let that throw you off. So what I need to take is the derivative of r with respect to t, r squared. So I'm going to bring my 2 down, so it's going to be 2 pi r, well that would be the derivative of r squared. I need to multiply that then by dr dt. Okay, you see how that works out pretty nice because we already know what dr dt is. All right, we know what r equals. We can go ahead and plug that in. And then we are looking for, it's already set up, we're looking for dA dt. So all I need to do is substitute in and solve the problem. So dA dt, so the rate at which our area is changing when the radius is 4 is going to be 2 times pi times 4 times 1. Okay. So we're going to have our radius is going to be then, is going to be changing by 8 pi. All right. All right, our next example is we're looking at an air being pumped into a balloon, a spherical balloon at a rate of 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is 2 inches. Again, we need to decipher what they're asking us to find. We need to find, here again, there's that rate word, the rate of change of the radius. So I was saying we better find dr as with respect to time, dr dt. We're looking for dr dt. All right, and then we need to decipher what else are they giving us. Well, we know that we have a spherical balloon. That might be helpful. They also tell us that air is being pumped into that balloon with a rate of 4.5 cubic inches per minute. If you think about air being filled into a spherical balloon, we're talking about volume. All right. So why it's important that we're talking about a sphere is because we need to find. We're going to use the volume of a sphere, which is 4/3 pi r cubed. If you didn't remember that from your geometry days. So we're going to use that, and then they tell us that the volume is changing at a rate of 4.5 cubic inches per minute. So what they just told us then is they told us the rate of our volume, dV dt, is changing at 4.5 cubic inches per minute. 4.5, I like fractions better. How about 9/2? Okay. And then the last thing they told us, when it's changing at 4.5 per minute when r equals 2. So I think we have all the information that we can get from that equation, or from that problem. So let's go ahead and try to solve for dr dt, given that we have dV dt and we have r. So let's take the derivative with respect to time. All right, t time. All right. So when I take the derivative of v, it's going to be 1 times then the derivative of v with respect to time t. So dV dt. And then 4/3 is just constant. Pi is just a constant. It's multiplied by this r cubed here. So I have 4/3 times pi times, I bring my 3 down, decrease the power by 1. But I remember I'm taking the derivative with respect to t, so I need to multiply by dr dt. Now I can simplify this a little bit. We can cancel our 3's out. So what I have now is I have dV dt equals 4 pi r squared dr dt. Whoops, dt. If you notice, all right, we know what dV dt is. That's 9/2. We know what r is. That's going to be 2. And we're looking for dr dt. So let's just go ahead and plug stuff in. We got 9/2 equals 4 pi times 2 squared dr dt. And let's just get dr dt by itself because that's what we're asked to solve for. All right, so I got, this is 4, so I have 16 pi. And when I divide that over, I'm going to have 9 all over 2 times 16, which is 32 pi equals dr dt. If I had a calculator, I'd tell you what the decimal is, but I don't. 9 over 32 pi is good enough for me. All right, so that is the rate at which the radius is changing. All right, when r equals 2 and the radius is 2. Excuse me again. Last problem here. Okay. It says an airplane is flying on a flight path that will take it directly over a radar tracking station. if s is decreasing at a rate of 400 miles per hour when s equals 10, what is the speed of the plane? All right, so let's look at what they're telling us. If s is decreasing at a rate of 400 miles per hour, here's that rate word again. All right, and it's talking about s, so we know ds dt equals negative, since it's decreasing, negative 400 miles per hour. All right, when s equals 10, so we know that s equals 10. What is the speed of the plane? When we talk about speed, we're talking about horizontal speed. So what we're really looking for is we're looking for x. We're looking for horizontal speed when we're talking about speed. So I'll tell you that. It's maybe something you learned here, but when we talk about speed in a problem, we're talking about the horizontal, and that's obviously our x. All right. So we're looking for the rate of change of x, dx, dt. Okay, well, now what? Let's think about this for a second. When s equals 10, I can sure figure out what x is going to equal. All right, by the Pythagorean theorem, right? So I can go 6 squared plus x squared equals 10 squared, right? So I get 36 plus x squared equals 100. X squared equals 64. X equals 8. All right, so I have another condition for myself. When s equals 10, x equals 8. I can use our same Pythagorean theorem now to figure out what dx dt is given these conditions right here. So let's use the Pythagorean theorem as our equation, because that's when I look at that problem, I need to use the Pythagorean theorem. All right, that's what I did. So I'm looking for dx dt, and the Pythagorean theorem says it's going to be, when we don't know x, we don't know x squared plus, and we don't know s squared, but we know he's going to be 6 miles above. So let's take the derivative with respect to t. So I'm going to have 2x dx dt plus 2s. I hate when they use s's and 2's and all that, so I'm going to write my s as a cursive s. 2s ds dt, and obviously the derivative of a constant is just 0. Well, I'm looking for dx dt, but I already know what, in these given conditions, I know what x is, I know what s is, and I know what ds dt is. So let's go ahead and let's plug that in. So let's go 2 times 8. 2 times 8 dx dt equals 2 times a negative, or 2 times s, which is, 10. ds dt, which is a negative 400, and that all equals 0. So this is a plus sign. So I have 16 dx dt plus, let's see, 4,000, negative 8,000, negative 8,000 equals 0. All right, well, let's go ahead and solve. Let's bring my 8,000 over and divide by 16. So I have 8,000 over 16 equals dx dt. And obviously we can simplify this. This can be an 8, this can be a 4,000, this can be a 4, and this can be a 2,000. This can be a 2, and this can be a 1,000. And this can be a 1, this can be a 5,000. So our speed is changing then at a rate of 500 miles an hour. So there we go. Hope this helps. I got to wrap it up because YouTube won't let me upload much longer. So I'll have another example for you at some point, but I hope this gets us to a good start. We'll see you in class.